A rope that is at 30 degrees to the horizontal is used to pull a 10 kilogram crate across a rough floor. The crate is initially at rest and is dragged for a distance of 4 meters. The tension in the rope is 50 newtons and the frictional force opposing the motion is 20 newtons. Determine the work done on the crate by the person pulling the rope. Okay, I don't like this wording. The work done on the crate. Because, to me, work done on the crate would be the force applied multiplied by the distance the crate moves. What this question is actually looking for, what your textbook is actually looking for, is the amount of work the person is doing, rather than the amount of work being done on the crate. Okay? If you look at the wording, if you flick over your page and have a look at the wording for B, you'll see that it says determine the work done on the crate. Whereas that's exactly the same as what it says in A, determine the work done on the crate. Okay, I don't like the wording here, but I've kept the wording because that's what the textbook has. Okay, so let's do it anyway. Determine the work done on the crate by the person pulling the rope. So first of all, is our direction of motion and our force in the same direction? No. So therefore, we need to use that other equation. Our work done is equal to Fs cos theta. All right, so the force applied is 50 newtons. Multiplied by the distance it has traveled is still 4. Multiplied by cos 30. Should be about 170 or something like that. Yep, 173. Call it 173.2. What's our unit? Joules. Okay, that's it. That's part A. So that's the amount of work that the person is putting into this. They're applying a force. They've dragged it 4 meters. So Fs cos theta. Okay. Okay, calculate the work done on the crate. So, for this, we can take the work on the crate and the distance moved as the same direction, that's fine. So, according to the crate, right, if the crate had thoughts and feelings, it is being pulled in that direction. So, it is being pulled in the same direction it's moving. So, we can consider those to be the same thing. However, we will need to resolve this a little bit. So we know that that is 50, and we know that that is 30 degrees. So therefore, we know that's cos. Cos 30 equals adjacent on 50. So our force is going to be 50 cos 30. Okay, I cannot get my calculator to give me a non-perfect answer. 43, thank you. 43 on the dot, 0.2? 0.3, thank you very much. All right, so the force in the same direction as the motion is 43.3 newtons. Okay, what have we not taken into consideration yet?
Distance.
Well, distance is one thing. Friction. There is a frictional force acting on this of 20 newtons. So we have 20 newtons pulling it back. So therefore, our net force is going to be 43.3 minus 20. So our net force is going to be 23.3 to the left. Okay, so now we've got our net force. We can use our work equation. Work is equal to Fs 23.3 multiplied by, and it's travelled 4 metres, which gives us 93.2 joules. Okay, last bit. Calculate the energy transformed to heat and sound due to the frictional force. Well, we know that the person has put in 173 joules. So the work done by the person is 173. Well, 173 point what? 0.2. Oh, this works out nicely. Joules. The work done on the box, or on the crate, is 93.2 joules. So that means we have our lost energy, which is our heat and sound, will be 173.2 minus 93.2. So we have lost 80 joules to heat and sound. So the person is putting in more work than the box is experiencing. So that work that the person is putting in that hasn't been transferred to the box has been lost to heat and sound due to friction. Okay, is that making sense? Yeah? All right, have a go at the next one.